Okay, so let's revisit this flux integral that we did last lesson. We had this vector field and then we were finding the flux across this paraboloid and the disk. So this, let me show you the picture from this. Well, not this one, here we go. Where we had the bowl and then its lid. And if you recall, in order to find the flux, we did these two surface integrals. So the first integral had all these steps. This is S1, and eventually we ended up with negative pi across S1. And then we had to go along the lid, S2, and we did all this work. I'm just going quick because you can see that video. Just want to remind you. And we ended up with pi across S2, so we added it together and we ended up with net outward flux of 0. Let's revisit this idea using what we know now, the divergence theorem. So my vector field here, it has continuous partial derivatives, you can tell, because you can easily take the partial derivative of each of the components and they're continuous. And this is a closed region because it's the bowl with the lid. So this is closed. So this tells us that the net outward flux through this whole surface, and so I'm going to call the surface S the union of S1 and S2, meaning S1 was the bowl, S2 was the lid, S is the whole thing. The net outward flux, we could use the divergence theorem and instead integrate the divergence over the interior, just the inside of the bowl. So let's find the divergence, and notice for this vector field, I'm going to take the partial of the I component with respect to x, so that's just 0, plus the partial of the j component with respect to y, and that's just 1, plus the partial of the k component with respect to z, which is -1, which is 0, everywhere. So this is a special type of vector field. It's called an incompressible vector field. And because of that, the net outward flux through any closed surface will be 0. And you can see then we just put in 0 to the triple integral and we're able to do that same problem from last time in 2 seconds instead of 2 pages. But that's a cool feature of any incompressible vector field. It's telling you that the amount in is always going to balance the amount out. So your net outward flux will be 0 because you don't have like gas expanding or contracting, or you don't have sinks or sources. So whatever goes in has to come back out and pass through equally. Before we're gonna do a lot more examples, I have a ton more for you to practice since this is a pretty big idea that we're ending the course with. But before we do that, I actually would like to make a cool connection to what happens if we take this idea of Green's and divergence theorem and bring it back down to 1 dimension. Okay, so what do I mean by 1 dimension? All right, by 1 dimension, I'm meaning I just have one variable that's describing my region. So let's just say that I'm looking at the interior of my region would be this interval. That means the boundaries of my region are just these endpoints, A and B. And I can define a vector field on this region, but in this case, my vector field will only have 1 dimension. So let's just let it just have an I component. We'll just call it little f of x, I. Okay, so the divergence theorem, if we were going to try to think of how we could break this down to 1 dimension, we're trying to say that the flux across the boundary is equal to adding up the divergence everywhere on the interior. So let's do the boundary piece first. Flux across the boundary. And then we want to say is equal to the sum of the divergence everywhere on the interior. We're going to see how we're going to get to that in just a minute. So flux across the boundary, I only have 2 points that are my boundary points. So I want to take f dotted with my normal vector. So notice my normal vector right here on this boundary is just going to be -I, and my normal vector here on this boundary is going to be I. So if I take the dot product, I'm just going to do f at Let's do it at the right side first, f of b, dotted with the normal vector, which is just I hat. And then I'm adding, because I want to find the total flux across the boundary, so I want to do the flux that I would get here at A, dotted with negative I. And that needs to equal, now if I go down to one dimension, I'm not going to be doing a triple or a double integral, I'll be doing a single integral of the divergence everywhere on the interior of the region. So this would be the single integral from A to B. But let's actually interpret this and see where it gets us back to. So this first quantity here, if I plug in b for x here and then take the dot it with the vector I hat, I'm just going to be left with little f of b. And then similarly, if I do that with this quantity, I'm going to be left with little f of a, negative little f of a. So I'll have minus f of a. And this is going to be equal to the integral. Now let's go see what the divergence is. The divergence, this vector field, is just going to be the partial derivative with respect to x of the I component, so just f prime of x. Ha, okay, and so this is, if we were to just try to break it down, we get to this. And you should be saying, wait a minute, I have seen this before, because you have in Calculus 1 and in Calc 2. This is actually the fundamental theorem of calculus. And so what's really cool is that the divergence theorem in Green's theorem is really just a higher dimensional version of the fundamental theorem of calculus.